Hello honors chemistry students, this is Mr. Spurk and this is your chapter 8 section 4 notes on polar bonds and molecules. So we've been talking a lot about covalent bonds, and we know that covalent bonds are when we share electrons, but covalent bonds do not always evenly share their electrons. The character of the molecule depends on the kind and number of atoms joined together. And these determine molecular properties. One of these really important properties is solubility. Think about oil and water. There's a very particular reason why they don't blend together or they don't mix together. They stay in two separate phases. And we're going to talk about why that is today. There are two types of covalent bonds. There are nonpolar covalent bonds and polar covalent bonds. So as far as nonpolar covalent bonds go, they have an equal sharing of electrons. There are two bonding atoms and they have similar electronegativities. Remember that electronegativity is the want or the attraction for electrons. So they can pull on those electrons within the molecule. And typically nonpolar bonds are between two identical atoms. So for example, we have Cl2. So here we have one Cl, and let's have another Cl over here. So we know so far that these two are going to share, and we are going to get Cl, single bond Cl, and they're each going to have two lone pairs. But we should remember that lone pairs and electrons don't necessarily just get locked into one place. Remember, we've learned about the electron cloud. So these electrons, however, we know that they are here, that this is where they spend a lot of time. These electrons are just zooming around these molecules. They're spending time with this chlorine, they're spending time with that chlorine, and they're equally sharing. That's why we see this diagram up here of these chlorine atoms. Each black dot that you see here is a center of each atom, so the nucleus of each chlorine. And this cloud represents their equal sharing of electrons. In a polar bond, we have unequal sharing of electrons. So one of the atoms typically has a higher electronegativity. And since electronegativity is the want or attraction for more electrons, it's pulling on those electrons a little bit harder. Think about tug of war. It's like the one with higher electronegativity is stronger. So it's going to pull that flag that hangs in the middle of the rope closer to its side. So one atom is, and what this does is it ends up making one atom partially negative and one atom partially positive. And this is what we call a dipole. It induces a dipole. So for example, if we have HF, we should remember that fluorine is the most electronegative atom on the periodic table. And hydrogen is all the way on the other side. It has a fairly low electronegativity. So even though that hydrogen and fluorine are sharing these electrons are spending most of their time with fluorine because fluorine is pulling them a little bit further towards it because it has a higher electronegativity. So if we look up here in the top right corner of the slide, we see an electron cloud depiction of what this would look like. You see we have fluorine atom here, hydrogen on the left, and you see that this is our electron-rich region because fluorine is more electronegative. And this is our electron-poor region because fluorine is a lot stronger. So fluorine's going to pull those electrons towards it. So there's an unequal sharing. So we can determine the type of bond, and the type of bond formed, we can determine it by the electronegativity difference. So here we have a chart that shows the different scales. So every element has an electronegativity value. And on the next few slides, we're going to see a periodic table that includes all those values. And all you have to do to determine if a bond is polar or nonpolar is just look at their values and subtract the difference. So for example, if that difference falls between 0 and 0.4, it's a nonpolar bond, which remember means the equal sharing. And if we have a value or a difference between 0.5 and 1.6, it's a polar bond, which is the unequal sharing, or one is pulling a little bit more than the other. And then we have 1.7 to 4.0. That's an ionic bond, remember, which is completely different from a covalent bond because we have a transfer of electrons. There is no sharing. So here is that chart for you, and we will look over that, and you'll have one of these for reference. So what type of bond is formed between a hydrogen atom and an oxygen atom? So what we need to do is look at their values. So oxygen has an electronegativity value of 3.5. Hydrogen has an electronegativity value of 2.1. So what we're going to do is just subtract them. So 3.5 for oxygen minus 2.1 for hydrogen gives us a value of 1.4. Now if we jump back and look at that chart, 1.4 falls in the polar covalent region. So the bond between H and O is polar covalent. And those electrons are going to be closer to the oxygen. Next up, what type of bond is formed between hydrogen atom and a carbon atom? So again, we look at the values. Carbon has a value of 2.5. Hydrogen has a value of 2.1. So 2.5 minus 2.1 gives us a value of 0.4. So again, we check our values on the table. 0.4 falls between a nonpolar covalent bond. So here we have a nonpolar bond. So we actually do see an equal sharing of these electrons. And lastly, what type of bond is formed between oxygen and oxygen? Well, O bonded to O, we have, if you remember from the last slide, 3.5 minus 3.5 gives us a value, 3.5 gives us a value of 0. So this again is a nonpolar bond. The oxygens are equally sharing their electrons. So we've talked about electron domains when we talk about VSEPR. Remember, that just means how many regions around that atom have electrons. So there are bonding pairs, which form the bonds in the molecule, and there are lone pairs. So if we remember, look at an example of NH3 or ammonia. Here is our lone pair, and our bonding pairs are these three sets of electrons. So we're looking for those within our atom or within our molecules. And we have to determine if the entire molecule is polar. So molecular polarity depends on the bonding polarity. So like what we just did with the electronegativity differences, and the shape of the molecule. So we're going to look for shapes that are symmetrical, which means it's the same on all sides. And what we mean by that is the same element on all sides. And asymmetrical, not the same on all sides. So we'll look at some examples of that. The shape of a molecule is caused by the VSEPR models. Remember that the valence electrons are arranged as far from one another as possible to minimize the repulsion between them. So, a polar molecule. A molecule is polar if it contains polar bonds. And remember, you're going to use the electronegativity values to determine that. A molecule is polar if it is asymmetrical, which means not the same on all sides. So if we draw out CH3Cl, we see that this is not symmetrical. We do not have all the same thing attached to the carbon. So that tells us that this is a polar molecule. Diving in a little deeper, remember that chlorine is very polar, or is very electronegative. So it's going to draw those electrons closer to it. And the last thing to look for, a molecule is polar if it has lone pairs on the central atom, like we see in ammonia. So the two key things to look for are the symmetry and lone pairs. Now, a molecule is nonpolar if it contains nonpolar bonds, and again, you're looking at the electronegativity differences, or if it is symmetrical. So in this case of CF4, or carbon tetrafluoride, all of these fluorines have the same electronegativity values, and they are all pulling on the electrons equally. Nobody is pulling harder than anybody else, so that makes it symmetrical. There are no induced dipoles. Therefore, it is nonpolar. This chart here represents the differences between ionic compounds and molecular compounds, so I'll give you some time to look over that. This is a great place to get familiar with these two different types of compounds. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great day.